Okay, so thanks very much for watching wherever you are. And this is going to be a talk about research on semifactual explanations. Specifically, the title is The Utility of Even If Semifactual Explanation to Optimize Positive Outcomes. This was work between myself and my collaborator, Wei-Peng Huang, whilst I was doing my postdoc at MIT and he was working at Tencent Security Research. So I just want to give a little bit of context before I get into this talk, because there are a lot of terminology in explainable AI. There's counterfactuals and semifactuals and all sorts of other things. And the first thing I just want to make clear is that a semifactual is not something that I've coined in the last few years. It's an idea which has existed in philosophy and psychology for the best part of a century, as I'm showing here in these Google Scholar citations. So just off of the bat as a preamble, I just wanted to make that abundantly clear that what this paper really is trying to explore what are the applications for semifactuals in computer science. So just as a bit of background in the potential of counterfactuals where there is a lot of research, a very popular application is when, for example, Alice might apply for a loan and might be rejected by an artificial intelligence system. And then people would use a counterfactual to explain how they may have had their loan accepted. However, the problem that I'm interested in is Alice applies for a loan and perhaps she's accepted by the AI. And in fact, there may actually be even better outcomes available to the user that they might not be aware of. And it's in this situation that we found semifactuals were actually quite useful in computer science. So the core challenges here is we want to optimize positive outcomes for users with explainable AI, so they gain something from the explanations. And this notion of gain is something I'll come back to again and again. And we want to show that such explanations are understandable and useful to end users, just as a very important component of explainable AI. It's something that's often overlooked. So we will be doing some user testing at the end. So just as a more graphical illustration, a prior approaching counterfactual recourse might have this canonical example of a bank loan rejected and accepted. And a user might be rejected when they can be given a counterfactual explanation saying, if you do X, we will accept your loan, which crosses a decision boundary. But in the semifactual situation, they might have a loan accepted, and the explanation could say something like, even if you want to halve your down payment, we will still accept your loan. So in this situation, they started in a seemingly good outcome, but they didn't know that there were actually better situations that they could have gotten into if they wanted to. So the goals of this research were, can semifactuals explain how to optimize positive outcomes for users? Can we capture the nuances of semifactual even if thinking? And this is with and without causality, which is something I'll get into later. And can we demonstrate the explanations again are understandable and useful to end users in user testing? So to get into the technical details here, we could define a semifactual function of three components here, just the individual X, a proposed action they might take A, and then of course a structural causal model. So if we illustrate this a bit more graphically, Alice here has her loan accepted. They will do some action A, adhere to some causal constraints, and then an outcome which is even better and possibly fairer outcome can happen with the semifactual explanation. And the fairness is something we considered for a while, in that quite often, for example, people might purposely not be told better outcomes that could happen. So the explanation actually can elude these better outcomes and in essence treat them fairer, which is especially interesting in and important in medical domains where, for example, people might be overprescribed medicine, and a semifactual can say, even if you want to halve your prescription, you would still be at low risk for a certain disease. And that's quite important because quite often people are overprescribed medications. So the optimization objectives here are that the explanation should be plausible in that it's in distribution, which is mostly taken care of by the structural causal model. The user should gain something from the explanation in a very real sense, which I'll illustrate more later. And as an aside, we want the explanation to be robust, and there should be several diverse explanations. These are things which have already been researched before, but we're just putting them in here as an important aside. So the main thing I want to emphasize here is this idea of gain. Take Alice again, where they have a loan accepted, but she would like to have a smaller down payment. If she takes an action A and decreases her down payment, she would experience positive gain. And likewise, if she takes an action which increases her down payment, she would experience negative gain. And that's basically how we define the notion of gain in this research. It's very similar to the idea of a cost function in recourse, where you're essentially trying to minimize the distance between crossing a decision boundary and where you are. A gain function is, in essence, trying to maximize that distance and not cross a decision boundary. So to get a little bit more technical, this is how we formalize the framework. The main difference between this and a typical recourse setup where you're trying to cross a decision boundary and minimize cost is that we're trying to not cross a decision boundary and maximize gain, which is where this is coming from. And this is the main part of the framework where we are taking as a function here plausibility and gain together. And we did this on purpose. We wanted to tie these two things together because if you, in theory, you could just increase gain forever and go off to infinity in some random direction in the feature space, but that might not be plausible. So an important consideration we chose to emphasize here in the formalization was that plausibility and gain should be dependent on each other so that you can't have high gain without plausibility and you can't have high plausibility without high gain. This is just a term for regularization, and this is some constraints about robustness and the structural causal model. So they are, again, they are things which have been researched before, and the main thing I would like to emphasize is the gain function again. But just to visualize this algorithm a bit more concretely, let's take again Alice here. She is this data point X where a loan has been accepted. Typically, a counterfactual would say something like, if you work 12 hours less, your loan would have been rejected. And that's where the bulk of research is focused. But in this work, we're focused on staying in the good side and trying to optimize it by saying something like, even if you double your repayment term and work 8 hours less, you'll still be accepted. Even if you triple your loan, you'll still be accepted. Even if you double your loan and double your repayment term, you'll still be accepted. And that is the main visualization here of the type of explanations we want to compute, all the while optimizing for this robust neighborhood around it, as well as several diverse explanations. So when I get into these tests here, I'm going to present results for two different versions of this algorithm. One is in a non-causal setting, just to make it more accessible as well. And in that situation, we just designed a normal genetic algorithm to optimize the explanations. And also because it handles categorical features very nicely, in my own personal opinion, it seems to work better for these kind of explanations. But the causality is also a very nice thing to have. And we primarily focused on that. And partly for reasons I'll get into again later with some of the results, it turns out to be really important as well. But for the purposes of these tests, we treated categorical features as real values. And for baselines, we chose two semifactual explanations in the literature previously, and one counterfactual explanation, DICE, that we just modified to produce semifactual explanations instead. And in the causal setup, we compared against two methods in the literature there as well, which we also had to modify to produce semifactuals instead of counterfactuals. So the metrics of interest, primarily again, I'm just going to focus on gain. That is the novel thing we're focusing on here. And that is essentially how far the generated explanation is from the user. The further away it is, the better, but not at the expense of something like plausibility, which I'm getting to now. In this case, we measured plausibility on how close the semifactual is to real training data. But in the causal setting, the causal model takes care of plausibility automatically. And robustness was another thing we emphasized. Um, in that, is the area around the explanation the same prediction as the explanation? Is there a robustness so that like a few months from now, the same explanation would still have the same outcome for the user if they were to take actions with it? And lastly, the diversity as well, in that we want to see, can we give a wide range of options to people? So these are the results for the non-causal tests. There were four methods here on the right. You can see our method SGen, which just stands for semi-factual genetic algorithm, and then the modified version of DICE and two other semi-factual methods from the literature. Overall, we found that even compared to the semi-factual methods, which were actually optimizing for something similar to gain also, the method we actually produced actually did a lot better on that metric. On the left here, you can see the white bars soaring above the other metrics. And similar things happened for robustness and diversity, but plausibility was a bit different, that we seemed to do worse when we were just doing one explanation, but then it gradually improved over time with more diversity. The x-axis here, M, refers to the amount of semifactuals that were produced. So, but probably more interesting actually are the results in causal tests. This is two data sets, Compass and Adolescentis, and our method SGen, this time it's using a causal model, is being compared to these two metrics. And importantly, we're considering the gain from the action as well as the causal gain. And what I mean by that is when you take your action where you might change one feature, you get a certain amount of gain from that. But then when you consider the causal relationships, it might change two or three other features. So when you add all that together, we're calling it the causal gain here. And I'll just draw your eye to this part because this is the most interesting part of the two plots. Just basically showing that our method actually has significant differences between the action and the causal gain. And it just hints that when you're doing these kind of calculations in reality, in deployment, it is likely going to be extremely important to consider causality. Otherwise, the calculations for gain are just not going to be accurate. So the last experiment I'll talk about is a user study where we wanted to compare showing people loan applications which were accepted and rejected with both counterfactual and semi-factual explanations to see which people found the most useful. This is an example of the type of questions we showed people, where, for example, Kate had her bank loan accepted, and we showed them these four features. And then we said two possible things a bank clerk could tell her are option one, which is the semi-factual explanation, explaining how to optimize that a bit better, and the counterfactual explaining how it could have been rejected. And then we asked them to rate how useful each of these two options were on a Likert scale from 1 to 5. And we did this for 3 questions. And then there was another 3 where they were rejected loans. And again, we showed semi-factuals and counterfactuals. And these were the results. And what happened was surprisingly a really interesting interaction between the type of loan application and the type of explanation, in that there was an interaction between the explanation type and the loan, between accepted or rejected. And semi-factuals were seen as significantly more useful when loans were actually accepted. But the opposite was true when loans were rejected, when people found counterfactuals to be much more useful. And if you think about it, this makes a lot of sense, because if you have a loan rejected, people generally find it more useful to be told how it could have been accepted. So for example, you might say if you had, earned 5K more this year, maybe we would have accepted it, rather than if you'd earned 2K more this year, we still would have rejected it. People didn't find the second one to be as useful. But when the situation was flipped, they found the semi-factual to be much more useful than the counterfactual, which was a really interesting finding. So the takeaways I'd like to highlight, rounding this back to the start of its talk, is that semi-factual reasoning can be used to effectively optimize positive outcomes, and to a certain extent, you could argue fairness for users. Causality does appear to be important to capture those nuances of even-if thinking as measured by the gain function we introduced. So it does appear that um, in order to accurately calculate these things, it is important to consider causality, and that does make a significant difference in reality. And lastly, in real user testing, people do genuinely find semifactuals more useful when they have a bank loan accepted. And I suppose in a more general sense, this might generalize to just any positive outcome in general. For example, in a medical domain, you could be told that, you're at low risk of a certain illness, but even if you want to halve your medication, you'll still be at low risk of that illness, for example. Or in the loan setting, you've been accepted, but even if you want to halve your down payment, you'll still be accepted. Or the last example I'll use is in a smart agriculture context where you could say to farmers, for example, your crops will grow a lot, but even if you want to halve your nitrogen usage, they will still grow the same, which turns out to be quite important actually, because nitrogen is a big contributor to climate change as it leaks from the soil when it's used too much. So I would envision a lot of applications for these type of explanations in the future, but we decided to focus on bank loans here as that's closest to the usual counterfactual research. And with that, I can round up this talk, and I hope I was able to teach you something, and I hope you enjoyed it. And thanks a lot if you made it this far.